Early in the war, Britain fielded a tank that did not depend on its gun. Instead, it carried a concealed arc lamp capable of blinding entire enemy columns at night. The system was kept highly classified. Most opposing crews never understood what hit them. The Canal Defence Light program began under secrecy. British planners examined night engagement deficiencies. Conventional headlights exposed armored vehicles to return fire. Engineers proposed a shielded high-intensity searchlight system. And the concept required integration inside an armored turret. Initial design studies evaluated available tank chassis. Medium tank platforms offered sufficient internal volume. Turret modifications became the primary engineering challenge. Design teams specified a high-output carbon arc lamp. Electrical demand exceeded standard vehicle generation capacity. Auxiliary generator units were therefore incorporated. Internal mounting brackets secured the arc lamp assembly. Whose reflector geometry focused the projected light beam. Engineers narrowed the output through a vertical slit. The slit width remained tightly controlled during trials. Shutter plates were installed ahead of the aperture. These shutters cycled rapidly during illumination bursts. The pulsing effect reduced enemy visual tracking accuracy. Cooling airflow became an immediate technical concern. Arc lamps generated substantial internal heat loads. Ventilation ducts were added within the turret housing. The thermal testing revealed persistent overheating risks. Additional insulation protected nearby electrical wiring. Power routing required heavy-gauge internal cabling. Cable insulation used heat-resistant rubber compounds. Switchgear panels were mounted beside the operator position. The operator controlled both lamp and shutter systems. Crew training emphasized strict light discipline procedures. Internal space constraints forced ammunition stowage changes. A standard turret armament was removed entirely. External appearance was deliberately kept conventional. Camouflage considerations remained a standing requirement. Prototype vehicles underwent controlled night evaluations. Testing measured glare intensity at varied distances. Observers recorded temporary visual disorientation effects. However, dust and smoke reduced beam effectiveness. Environmental sensitivity became a noted limitation. Electrical reliability issues appeared during early trials. While generator belts failed under sustained load conditions, reinforced belt materials improved service life marginally. Maintenance intervals remained shorter than desired. Water ingress threatened exposed electrical components. Sealing gaskets were redesigned repeatedly. Field trials included simulated battlefield conditions. Operators practiced coordinated movement with standard units. Communication procedures required careful standardization. Some crews reported internal visibility complications. A reflected light occasionally affected the operator station. Interior shielding panels were subsequently installed. Manufacturing responsibility fell to selected contractors. Production numbers were intentionally restricted. Security classification limited widespread documentation. Logistics planners prepared specialized spare parts kits. These kits included replacement carbons and shutter springs. Carbon electrode wear required regular inspection. The replacement intervals varied with operating duration. Supply chains struggled to maintain consistent availability. Procurement officers flagged material bottlenecks. Priority ratings shifted repeatedly during wartime planning. Deployment doctrine emphasized surprise night operations. Units trained to illuminate suspected enemy formations. The system proved highly situational in value. Daylight operations offered no meaningful advantage. Command reviews questioned overall strategic flexibility. Nevertheless, limited production continued under secrecy. Vehicles were issued to carefully selected formations. Operational feedback remained mixed across reporting units. Maintenance burdens remained persistently high. Electrical complexity exceeded typical field repair capacity. Specialist technicians were frequently required. Spare generator assemblies consumed valuable transport space. Some field units reported mechanical downtime concerns. The program administrators compiled periodic performance summaries. Post-trial assessments highlighted narrow tactical usefulness. Despite limitations, the concept demonstrated technical feasibility. Further development proposals were eventually deferred. Archival records retained strict classification for decades. Later evaluations examined alternative arc lamp models. Engineers compared carbon compositions for luminous stability. Electrode erosion rates varied between suppliers. But procurement files documented inconsistent manufacturing tolerances. Quality inspectors imposed tighter acceptance measurements. Reflector polishing procedures received additional attention. Surface imperfections reduced projected beam uniformity. Metallurgical reviews refined reflector substrate selection. Silvered coatings replaced earlier experimental finishes. Reflectivity gains improved measured output efficiency. However, coating durability remained a maintenance concern. While field vibration accelerated surface degradation, shock mounts were added beneath the lamp cradle. Rubber isolators reduced transmitted mechanical stress. Test crews monitored oscillation under cross-country movement. Data indicated partial improvement in component longevity. Electrical control circuits underwent further simplification. Complex relay assemblies caused intermittent failures. Engineers replaced several multi-contact switches. Simplified wiring harness layouts reduced troubleshooting time. Maintenance manuals were revised repeatedly. Technicians required additional familiarization. Training. Instruction pamphlets specified precise shutter timing checks. Misalignment produced irregular light pulses. Optical calibration tools were issued to units. Calibration procedures increased pre-mission preparation time. Commanders noted extended readiness delays. Transport planners evaluated deployment weight penalties. When the modified turret added measurable mass overhead, suspension components experienced elevated wear rates. Workshop reports recommended reinforced road wheels. Spare wheel allocations increased logistical burden. Fuel consumption rose modestly during field trials. Operational radius calculations were updated accordingly. Night maneuver exercises continued through late evaluations. Results confirmed strong frontal glare effects. Flanking illumination remained comparatively weaker. Doctrine writers adjusted recommended engagement angles. Coordinated unit drills attempted synchronized exposure bursts. Timing discipline proved difficult under battlefield simulation. Crew fatigue contributed to occasional mistimed cycles. Further automation proposals were briefly examined. Budgetary constraints prevented major redesign of Barzan approval. Inter-service reviews questioned overall cost-effectiveness. Some planners advocated conventional illumination alternatives. The program defenders emphasized psychological disruption value. Comparative trials with standard searchlights were conducted. Unshielded lamps exposed vehicles to immediate detection. The shuttered system retained measurable concealment advantage. Even so, maintenance complexity remained unresolved. Late war production priorities shifted elsewhere. Procurement orders gradually declined in frequency. Several incomplete units remained in storage. Post-war technical committees reviewed accumulated data. Reports acknowledged the system's narrow applicability. Archival disposition instructions followed soon afterward.